So hello, good day or good night to you. We're going to look at this example where we have an 8-bit word stored in memory, and we're going to use the Hamming algorithm to determine the number of check bits required and the check bits required to go along with this word to be stored in memory. So the first step is to determine the number of check bits needed, and to do this we use the formula 2 to the k minus 1 must be greater than or equal to m plus k, where k is going to be equal to the number of check bits and m is going to be the length of our word stored in memory. So we have to find a number for k, a value for k that satisfies this inequality, and we want this number for k to be as small as possible so we can lower the complexity of the problem. So we can do this by trial and error. Let's start with 3. We're going to have 2 to the 3 minus 1 on this side, and then we have m is 1, 2, 3, 4, 5, 6, 7, 8 bits, and k is 3, so that gives 11. This is 8, so 8 minus 1 is 7, so this is not greater than or equal to this side. So let's try k equal 4. So I have 2 to the 4 minus 1, and on this side we're going to have 8, and our check bit is 4, so we have 12 over here. 2 to the 4 is 16, minus 1 is 15, so this works. So we're going to work with k is equal to 4. Alright, so we're going to do steps 2, 3, and 4, and in these steps we're going to create the bit positions, insert check bits, and data bits. Now, first we need to know how long our code word is going to be. And to determine this, we're going to say that the code word must be equal to the m bits in the stored word plus the k bits that we're going to use as our check bits. So if you remember from step 1, there are 8 bits, and we said that k must be equal to 4. So our code word must be of length 12 bits. So we're going to make our bit positions. And we need 12 positions. Alright, so 12, 11, 10, now the next step is getting the binary representation for each of these positions. How we're going to know where we're placing the data bits and the check bits? We first put in the check bits, and what we're going to do is we're going to look for the binary representations that has only one within the binary representation, or simply put, powers of 2. So 2 to the 0, that's 1, 2 to the 1, that's 2, 2 to the 2, that's 4, 2 to the 3, that's 8. And we're going to call this check bit 1, check bit 2, check bit 4, and check bit 8. We get these numbers from the actual decimal representation. So it's not check bit 1, 2, 3, and 4, but 1, 2, 4, and 8. The next step now is just simply putting in the data bits that we have in this word. So we say this is data bit 1, data bit 2, data bit 3, 4. Step 5 is to calculate the formula, the general formula for each check bit. Now we're going to start with check bit 1. And to determine what data bits we add, we simply look at the binary representations and we look for each data bit that has a 1 within the 1's position. So in this case, you have that data bit 2, data bit 4, data bit 5, and data bit 7. So to calculate the check bit 1, we're going to exclusive OR data bit 1, we follow the same procedure for check bit 2, and now we're looking at the binary representations, and we're looking for each position that has a 1 in the 2's place. So as you can see, it will be this one, this, 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 and this. So that is data bit 1, exclusive OR, data bit 3, data bit 4, data bits 6 and 7. Alright, so now for check bit 4, look for the representations that has a 1 at bit 4, and that is check bit 2, data bit 2, data bit 3, data bit 4, and data bit 8. So 2, 3, 4, and 8. Alright, let's just up here for check bit 8. And again, 1's in the 8th position. So that's 5, 6, 7, 8. Now to actually calculate the check bits for this one, we know that this is data bit 1, 2, and so on, right up to data bit 8. So to determine the check bit for check bit 1, to determine the number of bits, determine the bits for check bit 1, we're going to exclusive OR 0, 1, 4, and 0 again, and 1. Now a quick note on exclusive OR. In exclusive OR, the only time that we'll get a 1 is when we have only one bit being a 1. So if you have two zeros, then that's going to be 0. If you have a 0 and a 1, it's going to be 1. If you have a 1 and a 0, it's going to be a 1. If you have two 1s, it's going to be 0. So we must have an odd number of 1s in order for it to be 1. So coming back to this, we have 0, exclusive OR 1, which is 1. 1 exclusive or 0, still 1. 1 exclusive or 0, still 1. 1 exclusive or 1, which gives 0. Check bit 2. You have data bit 1. Data bit 3. Four, 6, and 7. So 0, 0, now 0, 0, 0, 0 exclusive of 1 gives us 1. Check bit 4, we are going to use 2, 3, 4, and 8. So that's 1, 0, 0, and 1. 1 exclusive or 0 gives us 0. Sorry, 1 exclusive or 0 gives us 1. 1 exclusive or 0 gives us 1 still. 1 exclusive or 1 gives us 0. Finally, check bit 8. We're going to use 5, 6, 7, and 8. So that's 0, 0, 1, 1. So 0 exclusive or 0 is 0. 0 exclusive or 1 is 1. 1 exclusive or 1 gives us 0. So we have check bit 8, check bit 4, check bit 2, check bit 1, and 8 is 0, 4 is 0, 2 is 1, and 1 is 0. So to write back our word now, we're just going to follow this format. So at this point, we've actually answered the question, because it asks to determine what check bits will be stored in memory with the data word. So these are actually check bits. But to get a better idea of what is actually sent into memory, we can fill in the check bits along with the data word to show this. So in this position, we're going to put our check bit 0, our check bit 1, which is a 0, our check bit 2, which is a 1, our data bit 1, which is 0, our check bit 4, which is a 0, data bit 2, which is a 1, data bit 3 is 0, data bit 4 is 0, 8 is a 0, and 5, 6, 7, 8. So we have 0, 0, 1, 1. So this is the actual word, or the code word that is stored in memory. So we started out with 8 bits for our stored word, and we added our 4 check bits. So now instead of 8 bits, we have a code word of 12 bits being stored in memory.